Okay, so we're going to use the same kind of scenario where we're going to be shooting our projectile off a cliff. But like I mentioned before, what we're going to do this time, we're going to shoot a little bit of an angle. We'll say 20 degrees. All right, so I'm going to come in here and say my angle theta is 20 degrees. So now let's draw our picture here. Here we go, just like that. And we got H is up here. And our little cannon now is aimed up 20 degrees. Okay, so that little angle in there is 20 degrees. So now it's going to kind of go something like this. Okay, and we're going to ask the same question. We're going to say, okay, given that those parameters are all the same, except we're going at 20 degrees instead of 0, how far does it go now? Okay, how far does it go now? So what we're going to do is, again, we'll start by breaking it up into vertical and horizontal components. So I'm going to start my analysis with the vertical aspect of things. And so what we are going to have is same thing, R, the X component of the launch speed, okay, or the muzzle velocity, maybe we might call that thing. And then we got, of course, our delta T on here, okay. And if we go and get the vertical stuff, okay, we're going to have delta Y, V naught Y, delta T minus a half G delta T squared. Okay, just like this. Alrighty, now a good thing to do when you know your launch velocity, all right, and when you know your angle, is to go ahead and figure out what is the value of V naught X and what's the value of V naught Y. Okay, so when we launch this thing, okay, it's coming off here at some angle. So there's V naught. And so we're going to have some components. Here's my V naught X. And then I've got this bit here, which is my V naught Y. Okay. And so you can see the V naught X is going to go as the cosine of my angle. And the V naught Y, that component, will go as the sine of my angle. So up here, then I'm going to have V naught cosine theta. And here I'll have V naught sine theta. Okay. All right. Now, so I would just take 40 times the cosine of 20, and then 40 times the cosine of 20. Sorry, 40 times the cosine of 20, and then 40 times the sine of 20. I'm not sure what came out of my mouth, but that's what was supposed to come out. And when I do that, I get that my X component is 37.59 meters per second. And then the Y component is 13.68 meters per second. Okay. And again, really we want to limit these things to 3 sig figs, but this is an intermediate number. It's in between. So I'm going to throw an extra digit on there just to help my precision just a little bit more there. Okay. Save on some rounding errors. Alrighty. So the 3759, I'm going to stick in here, okay, for that. So once again, we're in that situation where if we knew what the time was, then boom, the range would pop right out of that thing, okay. But we don't know what that is, but we can get it by looking at the vertical aspect of our motion, okay. So there's my number there, okay, and we know delta Y is still minus 20. It's our minus H value, okay, and so let me write all that out. If we plug some stuff in there, okay, so I'm going down 20 meters, and then I'm going to have 13.68 meters per second, and that's going to be times. And that's going to times some time, which is going to be seconds, of course. And then minus a half 9.81 meters per second squared, and my delta t squared. Okay, now units wise, the seconds in here is going to cancel that. I'm going to have seconds squared, which is going to cancel that. So everything comes back to meters for me. I don't know what that squiggle is. There we go. That feels better to me. Okay. All right. At that point, then I've got a quadratic equation to solve and it's going to be very common. I would suggest that you figure out with your calculator or how to solve these quadratic equations with your calculator. All right. You could use alpha. Okay, Wolfram Alpha if you wanted to. Okay, lots of ways to do that. I'm sure you could find plenty of online calculators if either your calculator won't do it or you're not sure how to do it. Okay, pretty easy to do. But I do recommend you figure out how to do it on your own calculator, okay? Because you can use that on the test. Well, once we do figure all of that out, okay, with our calculator, what we end up getting for our delta t is two numbers. We end up getting minus 1.059 and 3.848. There we go. Okay. So let's talk about those numbers. What are we doing? Okay. Well, remember when you've got a quadratic equation, okay, when we've got something here, like this equation right here. All right. If we look at this thing as a function of t, all right, then what we're going to have is basically an equation that if we graph it, it looks like this. Okay. And once we solve for our values, we're solving for the roots. Okay. That's what we're actually doing. And that's going to be over here and over here. So this number is our minus 1 point stuff. And then this number is our 3.8 stuff. Okay. So we're not interested in any negative time. So we just keep the positive root. All right. So we're going to choose 3.848 for our value there. All right. Now, once we have that time, we can take it and we're going to plug it in back over here. Okay. Alrighty, so V naught, X is 3759 meters per second. And we got our time, which is 3.848 seconds. All right, take a quick look at our units. Our seconds here cancels our seconds there, so we're left with meters. So that's nice. And when we plug everything in, and again, I want to encourage you to do these calculations for yourself. Okay, play along. If we were doing this live in class, I'd be pausing to give you a chance to do the calculation. Okay, again, you need that practice. You need to get good at it. Okay. And what we end up getting is 144.7. All right, and that's too many sig figs, so we'll bump it to 145 meters. Okay, just like that. Okay, piece of cake, piece of cake. Alrighty. Again, you can see though what we did is we ended up using, in this case, again, we used the vertical information as our clock, so that got our time. Then we used that time and plugged it into the horizontal. Okay. So they go back and forth. Now, a couple videos from now, I'm going to do one going the other way where you can see how we use a scenario where we might use the horizontal information as our clock, okay, to get the time of flight. All right, now, before we finish this out, let me ask you to think about this. What would happen if instead of being up, what if it were tilted down? So that when we fired our cannon, it actually fired like that. So it went like, pew, right down into the ground there. What would that change? Okay, what would that change? Well, it turns out, algebraically, it changes nothing. we do everything exactly the same way. Numerically, it's going to change this number here. And specifically, that is going to become negative 13.68. Okay? And so I would end up substituting in here negative 13.68. All right. And that's going to end up changing my time, and that's going to end up changing my range. Okay. But algebraically, okay, the physics of it and the algebra of it is identical. Okay. We would just put in a negative initial velocity instead of a positive initial vertical velocity. Okay. There we go. All right. So when we come back, we're going to answer this question, which is, how high in the air is this thing going to go? How high in the air is that thing going to go? All right. So that's next.